So, hello everyone, welcome to this week Rogers Efficient AI seminar. And today we're very glad to have the Professor Mohamed Abdelfattah is from the Cornell Tech to give us this talk about the hardware awareness. And he is currently assistant professor at the Cornell Tech and in the electrical and the computer engineering department at Cornell University. His research group is designing the next generation of the machine learning-centric computer system for both data centers and mobile devices. And he received a bachelor degree from the German University in Cairo and a master's degree from the University of Stuttgart and his PhD from the University of Toronto. After his PhD, he spent 5 years at Intel and Samsung Research. And he also received the several best paper and most influenced paper awards in like the prestigious FPGA conference, right? The FPGA and FPL. And now let's welcome our speaker to give us this talk, Fast and Hardware-Aware Neural Architecture Search.
Right. Thank you so much, Bo, for the introduction, and thank you for inviting me to the seminar. As Bo said, I'll be talking about neural architecture search mainly here and how to make it really efficient and really geared towards hardware devices. So in terms of motivation, just looking at the compute volume that we need for DNNs, it's quite large. So if we look at ResNet 50, for example, we need 4 billion multiply accumulate operations to run a single image through ResNet 50 and to get the result out in terms of, like, for example, image classification. So if I have an image of a cat, and I want to label it as a cat, I need 4 billion operations. And that's a really big number. But an even more alarming thing is that if I want to improve my accuracy of this network in the same model family, I need to double the amount of computation to go all the way to ResNet 101. And this exponential trend is really alarming because it kind of prevents us from scaling machine learning or improving it further. I mean, if we compare all of this to how we were doing things previously, like before DNNs completely, we were building these like handcrafted features, for example, a histogram of gradient classifier. And compared to those 4 billion max, this was about 10 million multiply accumulate operations. So obviously there's a huge, order of magnitude difference between the way we used to do things before and deep neural networks. And this exponential trend of, improving accuracy costs us a lot of computation is very alarming as well. Now, part of the answer, I think, and part of the way to optimize these neural networks is broadly labeled as automated machine learning. And neural architecture search is a subset of that. And so people have been quite successful in achieving very similar accuracy to these very large networks with much more efficient networks by performing neural architecture search and by compressing these networks using various methods. And so this is mainly what I'll talk about today. There are other ways of also, getting efficiency out of neural networks, whether it's on the hardware level or the software level, but I'll mainly focus on this automated machine learning part. And so this plot is really nice, but it's a bit misleading as well, because I've been talking about image classification so far. And if we look towards other models, for example, in the language understanding domain, the state-of-the-art model there, or at least when I created this slide, this was state-of-the-art, it's much bigger. It wouldn't even fit on that plot. And so, it has 175 billion parameters. It requires 10 to the power of 23 flops to train. And that, if you just run this on AWS, it will cost you $5 million. And so, so a key thing here is, obviously, we do need changes on the algorithmic level and things using automated machine learning and efficiency. But we also need to go all the way down, to the software and hardware levels as well to get the most efficiency. I'll focus on the neural network layer in most of this talk, but I'll also jump down to the hardware layer and see how we can co-design the neural network and the hardware together. Okay, so most automated machine learning papers and work, you kind of hear about it from the viewpoint of a data center company, at least in the literature. The companies like Google have been very pervasive in publishing in this area. And so what does AutoML look like in a data center company? They have a lot of computers. They're a data center company. Google is estimated to have 1 million computers or 1 million servers. That's obviously a very large number. So they have a lot of spare cycles where they can run a lot of automated machine learning on it. They can try a lot of models and see which one is the best one and then use that. The other key thing is that their hardware is kind of uniform. So when they're optimizing a deep neural network, they want to optimize this DNN to work on a specific kind of hardware, which they have a lot of. And in the Google's case, it's usually the TPU. And so you have, very uniform hardware. So you need to run your neural architecture search or AutoML once for that hardware. And you have a lot of compute. So you can actually waste a lot of compute cycles in finding that ultimate best model, right? My perspective is very different because most of the AutoML work I did was at Samsung. And this is a very different company. It's a devices company, right? And in Samsung, they have tens, if not hundreds of different devices. Especially if we include kind of generations and tiers of their mobile phones, fridges, microwaves, vacuum cleaners, wearables, earphones, all of that stuff. And so the first key difference to a data center company is that now we have all of these different devices that we want to optimize models for. So if I'm taking ResNet 50 and I'm optimizing it, I need to optimize it 100 times for 100 different devices because each one of those has a different chip side of it and a different power envelope and a different battery and a different, heat envelope and everything. And so we need to take into account all of this, plethora of different hardware targets. The other major difference to a data center company is that we don't have data center. Actually, when we run expensive computations, we pay for it usually. Obviously, Samsung does have, good research infrastructure, but beyond that, it doesn't have any spare cycles of compute that it can just use at little extra cost. So we're trying to run everything on the device. We have many different devices, and we don't have the luxury of running NAS in large data center that we own. And so that's the challenge. So how do we make these neural networks hardware aware, customized for each different kind of hardware, and how do we do it really efficiently? And so that will be the main theme throughout my talk, especially in the first part, where I'll talk about efficient neural architecture search. Then after that, I'll talk a bit more about including hardware awareness. And finally, I'll go over 2 application case studies. Let's start with the first part. So I've been saying neural architecture search and AutoML so far, but what is that really? So neural architecture search is when we're trying to find the topology of a neural network. And the simplest way of doing that is through a sample-based search algorithm, where we have something that proposes a DNN structure. Usually that's some kind of search algorithm like reinforcement learning. It could be evolutionary search. It could be something else. And so we propose a neural network. In this case, it's this green neural network here. And then we send that structure for evaluation in another box. And here we just do training of that deep neural network. It gives us the accuracy. And the key thing is that we take this accuracy as a reward function or as a feedback signal back to the searching algorithm to basically improve it and allow it to propose an even better neural network in the next iteration. And so now we propose this golden one, and now the accuracy is 81%. And the idea is that we do this again and again and again and again until we find a neural network that has really good accuracy. And so the main problem with this is that it's slow. It requires a lot of compute. It has this thing called training, which is really slow and requires a lot of compute as well. And so how do we make this more efficient? And so I'll talk about 2 ways in which we successfully made this more efficient. The first one is to create more efficient search algorithms. And that will allow you to find better neural networks in fewer search iterations. And the second method is to use an inexpensive accuracy proxy. So instead of actually training to get accuracy, I want to be able to rank models or compare them to each other without finding the actual accuracy through full training. And so let's talk about these 2 things. Okay, so for the first one, to find a more efficient search algorithm, we kind of started investigating this idea of a predictor-based search. And what's a predictor-based search? A predictor-based search is that you have a model here. Let's just call it a predictor. You input the description of a neural network, and that model will output, the accuracy of that neural network. Obviously, you train it with a bunch of samples, so maybe you teach it through supervised learning of 100 different neural networks, and then for the 101st neural network, now you are trying to predict what that accuracy is. So this predictor-based search has been used in NAS as a searching algorithm successfully, and people have found that it works fairly well, not great, but fairly well. And then we took this idea of a predictor-based search and tried to improve upon it. And the first thing that we did is that instead of inputting just a single neural network to the predictor and finding the accuracy value at the output, we converted this regression problem into a classification problem, actually a binary classification problem in this case, but it could be extended to more than binary as well. And so what does that mean? That means instead of inputting just a single neural network description A, for example, we input two of them, A and B, and we ask our predictor to predict which one is better. So it's a binary classifier. The output's either 0 or 1, where 0 would correspond to A and 1 would correspond to B. And turns out that just by converting this from a regression to a classification problem, it becomes much easier to learn a model to predict, which neural network is better. And we're able to translate that into a real NAS search speedup. And so the key insight is, we don't actually need to know what the accuracy is while we're searching for the best model. We just need to know which one is better. And here is a plot that I'll show a lot today. So on the x-axis is a notion of time, how many models we actually need to go through full training for, and y is the best model we found so far. So in neural architecture search, that's the most important plot. And so red here is our binary relation prediction NAS, so this thing. And we show that we can improve upon the best previous sample-based search algorithm by a big margin. And so where do the gains come from? So let's take a closer look at this now. So our BRP NAS predictor looks something like this. We have two branches. Each one takes a neural network at the input, and then it tries to do a binary classification of which one is better. We actually use a graph neural network to extract the features from the neural network, from the input DNNs, and that worked fairly well for us because it has a notion of both the structure of the neural network and the node contents, which is the operation of the neural network cell. And so this is what it looks like. And just a reminder, if we are using just a single predictor, it will be just this part here, where we have one neural network going in and accuracy coming out. So this is what we call a vanilla predictor, which is what people did previously. And so if we compare, our binary predictor to a vanilla predictor, the accuracy is actually not, the accuracy improvement is not as big as you would expect, or not as big as I made it sound from the previous slide. And that's because this is only part of the story. So the main problem here is that we need to train our predictor for 100 models before we can start using it for NAS. And so we need to pay this upfront cost of 100 trained models. And so even though we get an improvement from our binary predictor here, shown in red, it still, it still has this extra fixed cost of 100 models before it can perform any search. So how do we get to a better result? Answer is in this slide. And so we performed this iterative data selection strategy. And so instead of actually waiting to train the predictor with 100 models all at once, we break down that 100 models into smaller pieces. So we train it on 10 models, and then we use that very weak predictor, very bad predictor really, to sort the rest of the models of my search space. And then we select the best models from my search space and then train again with another 10 models. And we do that iteratively again and again and again. And so what does that do? That basically uses a very weak predictor, slowly improving it by training it with more models. But instead of training it with just any randomly sampled models, it's training them with the models that we think are the best models in the search space. And so it's iteratively kind of gradually focusing on higher ranking models rather than focusing on just, training with 100 models from any part of the search space. And so this was the key insight that actually improves our binary relation predictor by a lot. And so if we compare actually the the rank correlation coefficient of the predicted accuracy with the ground truth, after performing this iterative data selection, the global rank correlation coefficient degrades. It goes from 0.9 to 0.85. So our predictor is now bad at ranking models across the whole search space. But if we zoom in on the best models, it becomes much better in ranking the top models in the search space. And that's what we want, because in neural architecture search, we actually want to find good models. We're not that interested in ranking all of the models to each other. We're actually really interested in honing in on those best models in the search space. And so now with iterative data selection, we get this solid red line here. And so it's kind of a synergy between both using, this binary relation prediction and this iterative data selection together, giving us a very big speed up compared to just binary alone or a normal vanilla predictor. And so, so this was the key insight here, where, how do we go towards more efficient search algorithm? We went towards this idea of a predictor-based search, and we improved it with this iterative data selection and binary relation prediction. And this is got us much fewer search iterations. And until recently, and I think until now, this is the fastest samples-based search algorithm out there, at least on a bunch of NAS datasets. And so the other thing I want to talk about is replacing training with an inexpensive accuracy proxy. So as long as you need to do full training to get accuracy, then your NAS will still be quite slow. And so how do we speed this up? So we looked into the literature to see what people are doing in terms of proxies for training. And it was summarized in a nice paper in CVPR a couple of years ago called EcoNAS. And they said that, in the literature, people have been doing various proxies, and they're mainly these reduced training proxies. EcoNAS did a good job of just, categorizing them into those 4 different categories. So people either, decrease the number of epochs of training, or use a smaller model, like by reducing the number of channels, C, or by using less training data, for example, or a lower input resolution. All of these things can make your training faster, while at the same time, it can give you some accuracy value that you can use in your neural architecture search formulation. So in the EcoNAS paper, they evaluated on 50 models, and they tried to find a formula with epochs, resolution, channels, and dataset, subsampling the dataset that would work well for neural architecture search. And they came up to this formula, which used 1/10 of the epochs, a quarter of the input resolution, a quarter of the model size. And they said, when we ran this on our 50 models, it correlated really well with the final training accuracy. The correlation was 0.87. And so that's great. And theoretically, this should be really fast because we're reducing training by a lot. We took this same proxy and we ran it on a much larger data set, NASBench 2, with about with many more models, like orders of magnitude more models, in this case about 15K models. And we found that this proxy doesn't actually correlate that well with final accuracy anymore. In fact, the correlation dropped from 0.87 to 0.61. So the first thing is that even though this proxy works well, this reduced training proxy works well for this data set, it didn't work well for another data set, so it wasn't really portable. And when we benchmarked it in actual wall clock time, it took time equivalent to 5 full epochs. And so this is because of just how training works and data transfers and loop iterations. And so there was a lot of overhead in actually running this proxy. And so we thought, okay, so if these proxies are already, not that accurate, so a correlation of 0.61 is not great, and they take a lot of time, can we find something that is also not that accurate, but takes much less time? And for that, we started looking at this idea of zero-cost proxies. At the time, there was this pruning at initialization literature that was really interesting, where they take a single mini batch of data. So, for example, you're training images, and they put it through a neural network. They compute the loss, and then they can compute an importance or saliency per parameter by just multiplying the derivative of the loss with respect to the parameter multiplied by the initial parameter value. And what is this? This is a way of gauging how trainable a neural network is by looking at gradient flow through the network at its initialization, at its initial state. And it works really well in pruning, or it works fairly well in pruning at least, in identifying individual parameters, whether they are important or not. So then you can prune unimportant parameters. We tried to do it per operation in a neural network, like per layer. And then we decided to also try to score entire neural networks to each other. And so that's what we call, zero-cost proxies. And we evaluated a bunch of different variations of that equation to evaluate the entire neural network. And basically what we did is that we summed over all of the saliencies of all the parameters in each neural network. And we thought, okay, let's empirically test this on NASBench 201 and see what we get. And so compared to EcoNAS, remember this reduced training proxy that people have been taking for granted so far, it has a correlation of 0.6 and it cost 5 full epochs to run. Our best zero-cost proxy had a correlation of 0.82 and its cost was just 1/200th of an epoch, even in terms of wall clock time. And so we felt like we were onto something here. So basically, we can evaluate a neural network at initialization just by looking at how gradients flow through the network, and we can compare topologies with fairly good correlation to final accuracy. Now, so far, we have just empirical data, empirical evidence that this could be a good way of evaluating NAS proxies or evaluating neural networks within NAS. But we have no guarantees, right? Like we don't know that this will always be a good predictor of final accuracy. So in our paper in iClear last year, we went ahead and we evaluated this on many different data sets. So instead of just NASBench 2, we did it on NASBench 1. We did it on models in the wild in NASBench and PyTorch CV. We did it on NASBench NLP and ASR and different data sets and different domains even. And we still found, a good signal that's coming out of this zero-cost proxies. And so at this point, we thought, okay, we want to integrate it within neural architecture search in very low-risk ways. And what does that mean? That means that even if the proxy fails, even if it returns a wrong result, the search algorithm should not, give us the worst neural network. It should still succeed. And so the two things that we did are called zero-cost warm-up and zero-cost move proposal. And let me explain that on an example search algorithm. So if people are familiar with evolutionary search, it looks something like this. So you have, an evolution pool. You initialize this evolution pool randomly with a bunch of deep neural network architectures. So if, for example, each one of those circles is a different neural network and then initialize it randomly. What happens in evolution is that, you take one of those neural networks, you mutate it into a different one. So you make a modification to that neural network, you train it, and then you put it back into the evolution pool. And because this is aging evolution, you usually evict or remove the oldest neural network, basically the neural network that was the pool for the longest time. So this is a baseline, search algorithm that works really well for NAS actually. And so how do we modify it? Okay, instead of initializing the pool randomly, we do this thing called zero cost warm-up. So if I need to initialize this with 16 different neural networks, I can take like 1,000 neural networks. I will score them all using these zero cost proxies, and I take the best 16 and put them back into the evolution pool. And so the idea here is that, I'm trying to bias my evolution pool to start with better neural networks. I'm trying to give my search algorithm a head start in finding good neural networks. But if they turn out to be, bad neural networks, then it's low risk. It's not a problem because, the evolution research will still kick in. I'll still find better neural networks. And so this is the first kind of low risk integration into NAS using our proxies. The second thing is zero cost move proposal. And here, instead of just, evaluating a single mutation of my neural network, I'm evaluating all possible mutations. So in some cases, these are like 25 different mutations. I can very quickly score them using zero cost metrics in like a matter of seconds or less than a second even. And then I take just the one with the highest zero cost score. And this is the one I actually do full training for and add back to the pool. And so these are two ways of kind of changing a baseline search algorithm that's already powerful and already good at finding, at finding neural networks. But I'm biasing it in the direction of choosing models with higher zero cost scores to help it kind of converge faster. So we actually do this for a bunch of different search algorithms, not just evolution. So I'm showing here for random search. The blue line shows the baseline random search, and these other lines show variations with our zero cost warm-up, zero cost move proposal. Here we show that we can improve by what is this? This is about 50 times faster in terms of at the same accuracy, or we can improve accuracy at the same time with 1.7%. So we can show kind of drastic improvements compared to baseline random search. But we also did it with reinforcement learning, and here we get a 25x speed up. With aging evolution, which I showed the example for, we get about a 10x speed up by integrating the zero cost proxies. And even for the binary relation predictor that I showed before, we integrated zero cost warm-up with that binary relation predictor, and we're able to speed it up by about 2.5x. And so so what did we do? We found this way of evaluating neural networks very cheaply without any training, and we managed to integrate it within neural architecture search in a very low risk way that always kind of resulted in the same or a faster neural architecture search process. So these are two ways in which we made neural architecture search faster. As I said, we're motivated mainly by the fact that we don't have a big data center to run everything, and so we need to run a lot of neural architecture search to customize for different devices. So we need to make it faster. I talked about BRPNAS, binary relation prediction, and these zero cost proxies to do that. And before moving on to the next section, I'll talk about very new work. So this is being presented right now, actually, at NeurIPS 2022. And so what we wanted to investigate there is that it's called Macronas. So far, with neural architecture search, people have been implicitly focusing on this idea of a cell-based search space. What does that mean? That means if you have a cell or a block here, the contents of that block, you can modify it, and that's what you actually search for. You search for what operations are between each node, you search for the connectivity and so on. But what happens afterwards is that you take that same block and you repeat it in the different stages of a neural network. So maybe if you have 10 stages, they all have the identical block within it. What Macronas is that it allows each one of those blocks to be different. So this can have, the contents of the cell can be different from the contents of this cell, can be different from the contents of that cell. And this can be potentially really powerful because it's a much richer search space. It can customize the cell or the block in different parts of neural network. But at the same time, the search space grows combinatorially, right? Like you have a huge search space now, which is even harder to navigate and needs even better and faster and more scalable search algorithms. And so we wanted to see if it's possible to do this Macronas for our different devices. And so we started with creating a data set called blocks. And I'll say more about that in a couple of slides or so. But first, why do we even want to look at macro neural architecture search? So first, we ran this simple experiment here where we have, flops or parameters at the x-axis, and on the y-axis we have accuracy. And so the blue dots here, or the blue triangles rather, they show the best models which have uniform blocks. So the same block is kind of stamped out through the whole network. Whereas the red squares are showing models that have different blocks. So in that case, the red block can be different from the yellow block, can be different from the green block. And so when we have this diversity of blocks, we can see that the Pareto front of accuracy here and flops is typically a lot better than when we have uniform blocks. In this case, it's 2% better, throughout the search space. The same idea with parameters. So moving towards this much more diverse search space, okay, it's a much larger search space, but it's also much more diverse. It has the potential to lead you towards finding much better models, and people have been not really paying attention to that so far. And so there is something to gain from going towards macro neural architecture search. So as I alluded to before, you can use normal sample-based search algorithms, things like BRPNAS or aging evolution or reinforcement learning, to find these macro neural networks or these different block neural networks. But at the same time, it's really inefficient or it's really difficult because the search space is now much larger. It's huge. And so there are these class of blockwise neural architecture search models that started to pop up. One of them is called Donna, one of them is called Lana. And in our paper, we actually analyzed those in detail in on our blocks dataset. And the key idea there is that you decompose the search problem into a blockwise problem. And so here is kind of just a cartoon of how this works. First of all, you gather these blockwise signatures. So what does that mean? It means I start with kind of this backbone neural network that has B0, B1, B2. And then I look for different candidates to replace each block of the neural network. And they can be different kinds of blocks in different stages. And that's why it's macro neural architecture search. And so here I'm trying to replace B0 with B01. So in the Donna paper, for example, what they do is that they perform blockwise distillation between B0 and B01. They take the distillation loss after, I think, 10 epochs or something, and then they use that as the signature of B01. They do the same for a bunch of candidates, in this case, M candidates, and then basically the one with the best, with the lowest loss or with the best signature is the one that wins, and that's the one that we replace B0 with. Okay, that's a simplification of how it works, but that's basically the idea, to do local search for each block and then combining things globally together based on the signatures extracted from this local search. And so I urge you to go and take a look at the paper for more details on that, because we do a really thorough study of how these algorithms work and how they compare to each other. But I'll just give a headline result here. And if we compare to BRPNAS again, which is the fastest sample-based search algorithm from before, to some of these blockwise, a specific variation of these blockwise NAS algorithm, we find that we can get to a better accuracy with the same search cost, or to get to the highest accuracy here, we can get to it much faster than a normal sample-based search algorithm. And so potentially there is a lot of potential from these blockwise search algorithms in handling these large macro search spaces. So as I said, there is a data set, we call it the blocks data set, that we performed all of these experiments on. And you can see it here, how it compares to other data sets. It has 91,000 models, so it's actually quite big. Maybe it's the third biggest or second biggest real NAS data set to date. And it's also one of only 2 macro search-based data sets. So yeah, if you think this is useful for your research, feel free to go to this link and you can use it there. I think we're putting the final touches on it now, but this will be available within days. So. Okay, so this was the first part about efficient neural architecture search. I talked about sample-based search algorithms, how to make them faster using prediction, specifically binary prediction and iterative data selection. I talked about proxies for training and how zero-cost proxies have the potential to speed up NAS even if they're inexact. And finally, I talked about blockwise neural architecture search and how that can be a very effective way of dealing with macro search spaces. Now, as I said, this is from a Samsung perspective and from a devices perspective. I'll talk a bit more about how to make the neural network more hardware aware, more customized for each different hardware target. And so far I've been talking about neural architecture search as a way to find neural networks with higher accuracy. But now we're going to add another objective, which is latency or speed of running that neural network on different hardware that we care about. And in the case of Samsung, this is going to be TVs and phones, as you can imagine. So how do we tailor neural networks to this hardware? So the first thing that we found that we needed to create was a good predictor of latency so that we can integrate a latency model into our neural architecture search problem. And when we look towards the literature, we found that people have been using the number of operations or flops as a proxy for the speed of a neural network. But when we measured this again on NASBench 2 in this case, we found that it was not a really good predictor. So at the same flops, you have very big range of latencies. I think this was on a mobile phone, as you can see here. So I mean, yeah, like this value of flops, your latency could be anything between 2 and 8 milliseconds, which is almost the entire range of latency. And so this was a really bad way of evaluating how fast a neural network runs. The next best thing, which people have been using actually quite heavily in the literature, is a layer-wise model. And so what is that? If I have a neural network with 1, 2, 3 layers, then basically you can measure the speed of each layer individually in a neural network. For example, 3 milliseconds, and then this one takes 5 milliseconds, and then this one takes 2 milliseconds. And then to find the total latency, you just add them up. And this works much better than flops as a proxy for actual runtime on a device. But still, it's not that accurate. So if we compare the predicted versus measured latency, it should follow, or it should track that y = x line. But here, it's not that accurate. And because there are many interactions between layers, certainly at the compiler level, but also at the runtime level, and where data sits, whether it's in the cache of your processor or whether it goes out to external memory, whether things can be optimized, like layer fusion between layers and things like that. So all of that is not taken into account. So our approach was, again, moving towards predictors instead of following this layer-wise model. And for that, we used the graph neural network-based predictor, where again, we trained it with a bunch of neural networks. We input the description of the neural network, and we output what the latency is expected to be after training it with a bunch of models. And here we were able to get to a much better predictor. In this case, 97% was within 10% of the actual measured latency, whereas compared to the layer-wise model, that number is 33%. And so more details of that again in the paper here. It uses kind of the same predictor topology that we use in the accuracy predictor from before, but we just use a single branch of it. And as part of that, we also open sourced a very large latency data set on 6 different mobile devices. And we also open sourced our GNN predictor. And so yeah, we found that this predictor-based approach was a much better way of finding neural network latency during the neural architecture search process. And yeah, so I mean, okay, so we have a good predictor. Why does it matter? And so key thing is always to show that this actually shows an actual improvement in end-to-end NAS results. And this is what this shows here. So again, we have trained models on the x-axis and best accuracy on the y-axis. We can show that, in this case, we just used aging evolution as our search algorithm. When we use the layer-wise model, it gives you this blue line here. So we never actually get to the best model. But when we used actual measured latency or our GCM predictor, they are really close and they both lead to much better models. So on end-to-end NAS, we do get actual improvement. So. Okay, so taking this even a step further, so we talked about adding latency to our NAS search problem to find neural networks that are not just accurate but also run fast on a specific hardware. What if we also want to search for a hardware architecture at the same time? So we call this co-design NAS. And the idea here is that we're using a very similar AutoML formulation, but now we're not just proposing a deep neural network. We are proposing a deep neural network and a hardware architecture at the same time. And we want to know the we want to create like both a hardware and a neural network pair that work together and optimize all of these metrics at the same time. So accuracy, latency, power, and area as well. So what did we do here? We wanted to just create a very simple proof of concept to see if we can outperform manually designed hardware. And for that, we took this simple neural network accelerator from Xilinx that was hand optimized for ResNet and GoogleNet, actually. And we basically parameterized it with the different things that you can change. So you could parameterize the buffer depth, the memory interface width, very simple things like the parallelism in the convolution engine and things like that. We paired this with a simple search space. Again, this was a cell-based search space, or a cell repeated 3 times in a stack, which was repeated 3 times, and you can only search for the contents of the cell itself. And together, these two search spaces give you 3.7 billion valid combinations. And so that's a big number. But when we looked through it and when we evaluated it, we found that just 3,000 of those were Pareto optimal points. So already we're getting an indication that it's hard to actually find those values, and it's unlikely that people will do that manually. But then, yeah, so we thought, automated search would be the way to do that. So we explored in the paper, we explored different multi-objective search strategies. So what do I mean by strategies? We have this separate, combined, and phase. So separate means, we search for a neural network, and then when we find the best one, we go and search for an accelerator architecture. And this is kind of the traditional way of doing it. You search for the neural network separately, and then you do design space exploration on the accelerator to optimize the hardware. And that's very typical, especially with FPGA hardware, where you can kind of optimize it after the fact. Combined is just adding both into a very large search space and searching for both together. And phase is when you do it in phases. So you search for a neural network for a little bit, and then for a hardware for a little bit, neural network hardware, and so on. And we found that both combined and phase yielded good results, with phase typically converging much faster, a bit faster than combined. But basically, they both were much better than separate search. And so this is what our search looked like. In that case, we used a reinforcement learning-based controller, where it would propose a neural network. Here it's proposing the different operations in a neural network, and then afterwards it will go towards proposing the different parameterizations of the hardware. So the pixel parallelism, the buffer depth, memory interface width, and so on. So And so here I'm showing kind of the headline result. On the x-axis, I'm showing a measure of efficiency, performance per area in this case, which is very similar to performance per watt, but we didn't have power measurements. And on the y-axis, we have accuracy. So we want to optimize both of those objectives. Here I'm showing the manually designed points by Xilinx. So this is for the ResNet cell, this is for the GoogleNet cell. And so we ran our search, gradually increasing the threshold performance per area that we allow. And after some search time, we found this network called COD1. And this was already better than the ResNet network on that accelerator, even when manually designed, by about 2% in accuracy and 40% in performance per area. And so already we can see that, just by putting these different parameters in the same search formulation, we're able to get to significantly better results on both accuracy and efficiency. We continued our search, and we also found another neural network that outperformed the GoogleNet design, although by a smaller amount. But I mean, the main thing is that this simple proof of concept showed us that just by including both the hardware and the neural network parameters and finding both together in a combined search formulation, it can get us, a much better result than manually or individually designing both parts. And all of this was by just simple tweaking of these hardware parameters, things like just editing the buffer depth and choosing where the area goes, whether it's in the filter phase parallelism or depth or whatever. And so this simple proof of concept, I think, just shows the promise of this idea of automated co-design. And I think especially when it comes to FPGAs and neural networks, I think this is a key design methodology that should kind of improve things by a lot. Yeah, I should also say that including more complex, more non-obvious hardware search spaces is the key thing to do next for this, because so far we just tried these very simple parameterizations, but potentially an automated search algorithm can find non-obvious hardware designs much better in a complex search space. Okay, and so that was the second part of my talk, just going over how we make our neural architecture search hardware aware, first by finding these accurate latency predictors, and we used graph neural networks for this prediction. And second, we went towards this idea of co-design, where we actually co-design both the hardware and the neural network together to optimize both. Finally, I'll give a quick overview of some application case studies. So did we actually use these technologies at Samsung? Yes, we did. And so I'll show two case studies of optimizing a super resolution model and optimizing a speech recognition model using some subset of the stuff that I talked about before. The first one, and these are two very important domains for Samsung, obviously, because TVs and phones are some of the main business of Samsung Electronics. And so these were published at ECCB and Interspeech a couple of years ago. And so with super resolution, at the time we were using this generative adversarial network. I don't think that's standard anymore, especially with the rise of these diffusion models. But at the time that was state of the art. And the idea there is that you have actually two neural networks used in training of that model. You have a generator network that takes as input just this random noise and tries to generate images, and you have discriminator networks that compares these images to actual ground truth images or real images and tries to just figure out whether it's real or fake. By doing this kind of discriminative training, people have found that they can create generative models that work really well. And super resolution is a key application in these generative models, where you interpolate basically between points going from 4K resolution to 8K resolution, for example. And why is this important for Samsung? It's because they create these really high-end displays that have 8K resolution or even more. but the content is still at 4K. So no one is actually shooting 8K films, but you have an 8K display. So how do you display this film on that display? You use super resolution. And so this is really important and part of all Samsung TVs, as far as I know. And so our key insight was that even though you will only use the generator after training is done, we thought that we would want to search for a generator network and a discriminator network that work together. And that was the key insight there that allowed us to get to up to 30 times smaller model with almost the same image quality. So we use this LPIPS image quality metric here. It's called the perceptual image quality metric. This plot here shows that the discriminator really matters. So this D1, D2, D3 are discriminators that we found using our neural architecture search, whereas these ones are kind of standard discriminators that people have used for other models. If we just took those, even if we find the best generator to work with, LPIPS was quite high, and high here is worse, so lower is better. Whereas when we automatically found discriminator that works well in conjunction with our generator, again, it's kind of co-design, then we managed to get to this better values of LPIPS. In this case, D2 gave us the best value. And so that was the key insight there. Compared to the state-of-the-art models, again, from 2 years ago, it was about 30 times more efficient and allowed us to run this kind of model within Samsung TVs with a very small drop in accuracy. The second case study I want to talk about is speech recognition. So in your phone, you usually have this Google Assistant or Siri or Alexa or whatever they're called. And at Samsung, it's called Bixby. And that assistant so far has been running on the cloud. And so whenever you actually talk into your Samsung phone, Samsung is paying the bill for running this query on a data center that they rent from AWS or something else, right? So, so this is obviously a running cost for Samsung, especially for their high-end phones. And so they really want to run these speech assistants on their device, on the processor that exists in their device itself. And so our challenge was to take this model and to try to compress it so that it can operate efficiently on the device. And for that, we tried this a simple compression method, which is low-rank matrix factorization. And so the model at the time looked something like this. It was an encoder-decoder attention-based model with a bunch of LSTMs in the encoder layer and some in the decoder layer as well. And so what we started with was, we're going to manually compress this using SVD. SVD is singular value decomposition. Basically, you find the matrix ranks and you keep removing matrix ranks towards a low rank matrix factorization, and then that gives you a compressed model. And so this plot here shows kind of our manual investigation, showing that the more we compress the model, so that's what we're showing on the x-axis here, the higher your word error rate. But it's actually different for different layers. So for example, the output layer was really sensitive, and as soon as you decreased, it was basically a full rank matrix. So as soon as you remove one of its ranks or one of its dimensions, it completely increases your word error rate. Whereas some models, some layers were much more tolerant to low rank factorization. So you can see here these attention layers, they were fine if you compress them by a lot. So basically we took this manual investigation and we tried to compress the speech model manually. And this is what I'm showing here. So this blue line shows that how much speed up on the x-axis and word error rate on the y-axis we're getting from manual compression. And here we just use the same matrix ranks for all matrices in the neural network. Whereas the black line here shows a much more intelligent one where we use this investigation to edit those matrix ranks based on the layer sensitivity. So we will not really compress very sensitive layers, but we'll compress insensitive layers much more. And then, so this is the black line. I can say with confidence that, it's very hard to do something better that is manual. And so this is what we can see with the black line here. And then these green dots are showing what happens with our neural architecture search. So obviously we also take these matrix ranks and put them as the parameters for our AutoML search. And so the AutoML search is now telling us what is the rank of each matrix that we should use. And here we're showing the search in the first 300 steps. Dots are all over the place. Some of them have really bad word error rate. Some of them have good word error rates just by virtue of the random search. But it's showing that as the search progresses, the models that we're finding are being clumped more towards models that strictly dominate this manual search. So a lot of these models that we found here through automated search are much better than the manual one. And so overall, after retraining, we were able to get to a compression of 3.5x from the manual search for matrix ranks, from the automatic search for matrix ranks, which was much better than what we could do with the manual one. And for this, we actually wanted to run the search really quickly again. And so in this case, we tried to evaluate our data points on a much smaller data set. So we went towards a reduced training proxy and reduced evaluation proxy as well, where we did something to our data set that we call it condense. And what that means is that we actually took just 83 samples from the Libri speech test validation set. And we chose those samples based on this condensed algorithm, which just finds the samples that have good correlation across a cohort of models. And so if I take 5 or 10 different models from my search space, and I run them all on this sample, then the output of those models is going to be correlated with each other. I also filtered it based on which samples are too easy. If samples were too easy, then I excluded those as well. So if the word error rate was already quite low on those samples, then I excluded those. So I took relatively hard samples which models agreed upon the result quite uniformly. And so we're able to compress the Libri speech validation set by 67 times, and that resulted in a proportional 67x improvement in our search time. And here we're showing the correlation of our small data set, or of the word error rate of our small data set, with the entire def clean, or the entire Libri speech validation set, when we use just random samples. This is the blue line. And when we used our condensed algorithm. So we were able to get to a data set, right about 87 samples here. That was really good and representative of the entire validation set. A further thing that we did was that, again, we ran our search and retraining iteratively. And so we set kind of a small speed up target, in this case 2x. We searched for the best matrix ranks, and then we did a bout of retraining to regain accuracy back. And then we set a higher compression target, in this case 3x, and then we did retraining, and then a higher compression target, and then retraining. And so this practically has allowed us to push our SVD-based compression previously without this iterative approach from 3.5x to about 5x by doing this iterative. And so overall, we were able to compress this Bixby speech model by 5x, and we think it's runnable on device. I don't know if it eventually made it to the device or if it's still run on the cloud, but it became much more efficient for sure. And so this actually brings me to the end of my talk. And so I started by talking about efficient neural architecture search. BRP, NAS, zero-cost proxies, and blocks, macro neural architecture search. Then I talked about how to make neural networks more hardware aware in the NAS formulation. So I talked about latency prediction and DNN hardware co-design as well. And finally, I went over these two application case studies where we show actual improvement on Samsung models that they really care about. Oh, and I should mention, this was not just my individual work. This was based on a lot of hard work by Ankai, Royson, Javier, Lucas, and Thomas as well, who were in my team at Samsung. So great team and lots of great work that we're still working together on, actually. So, so thank you, and I'll be happy to take any questions. So.
Thank you very much, Mohamed. Very great talk. And I think we have some question in the chat box. Can you see the chat box?
Yeah. Okay. So Chen, can you share some principles to the loss function design of co-design NAS and how to search the parameters related to the hardware by setting the limitations? So Chen, that's actually a great question. So for the loss function, tuning it was a bit of a trial and error thing. Basically, for any multi-objective loss function, things like accuracy plus alpha, accuracy plus beta, latency plus beta, power, something like that, tuning those values is very tricky. And so, so when you're doing an open-ended multi-objective search, you just need to do some trial and error to find those. The other thing that makes it a lot easier is to put constraints. And so actually in that, let me go back. In that plot here, I'm actually showing I'm showing unconstrained, one constraint, and two constraints. What does that mean? That means instead of performing a multi-objective search, I'm just putting a cutoff. And so in unconstrained, it's a pure multi-objective search. It's, the reward function has both accuracy, latency, and area in my reward. And I need to tune, the values exactly and how they are summed together or multiplied together or something. There are some ways to combine those using multiplication, some ways to combine them using addition. But by putting constraints, that means I will only accept results that are smaller than this area, for example, 2 millimeters squared. Or I'll only accept results that are faster than 2 milliseconds. And so by putting more constraints, you're able to eliminate you're able to eliminate search points much faster, and the reward function, there is no reward function engineering. Essentially, you can simply have a single objective search in the case of two constraints. So you can just search for accuracy or search for latency, and the rest are just constrained. You will not accept any result below that value. And so the second part of your question, how to search the parameters related to the hardware by setting the limitations. So, I mean, for the hardware, I think putting more flexibility into what is available to the search algorithms is better. Because this is automated search, the hardware may potentially find non-obvious solutions. And so I think the more the better, really. I don't think I would try to limit the hardware search space that much, because these search algorithms can handle fairly large search spaces. Obviously, if it's something that's clearly inferior or you can eliminate easily, then I wouldn't add that. So, Jin Chi is asking, as the number of candidate operations increase in the supernet, the GPU memory consumption will also increase when using gradient-based method. How can we reduce the search consumption? So, okay, so Jin Chi is asking about DARTs or differentiable architecture search and how to overcome GPU memory limitations. So there's the paper called Proxyless NAS, where they do sampling instead of training the full supernet at the same time. You can sample pieces of the supernet so that you don't need to store it entirely in memory. I think that's one way. What else? Yeah, I think that's the main thing that comes to mind. Xinqi. Zhao is saying, thank you. I have 3 questions. For the BRP NAS, why not use more models instead of 2 as input? That's a good question. I don't think we tried more models, but you can convert it into a multi-class classification problem fairly easily. We just decided to go binary classification. That's an interesting thing to try. I wonder if it will work better. But you can use multiple neural networks at the input. And it can still be, I guess it can still predict just what is the best one out of n. It doesn't need to rank the neural networks. It can be either predicting the best one out of n input neural networks, or it can rank them all. So it can say these 5 networks at the input, what is their relative ranking? But we haven't tried that, and I think it's a good idea to try. For the saliency map computed for the accuracy proxy, will it filter out parameters without enough saliency? If so, how to determine the threshold? So for the zero-cost proxy stuff, basically, you end up with a number representing a neural network. That number I'm calling saliency, or a sum of the saliency of the parameters. And so you can use it to kind of filter out bad networks. That's what we're using it for. But I don't really understand what you mean by a threshold here. So I'll punt this question unless you send me a clarification. Your third question is, will the temporal information be useful in producing better evolution pools, i.e. using LSTM to produce better network samples? I don't know what temporal information that is. You mean throughout the search? So usually LSTMs are actually used in reinforcement learning based controllers because there is temporal information, right? Because throughout the different samples, there is temporal information between them. And so you want to so as this image here conveniently shows, actually, in producing predictions from one part of the network to another, you are using an LSTM. And so, so the answer is yes, using an LSTM could help. Larry is asking, what is changing in the NAS? Is the model changing in a regular way, such as with, oh, that's a good question. So, Larry, everything can change. So let's see, in this search space, we are changing the operations here, and we're changing the connections. So we can change what operations are there and what connections there are. In other search spaces, you can change the number of channels in each layer. You can change the type of operation. Some search spaces we're working on now, we change the bit width of each layer, so the quantization. So you can change anything.
And so do you do that in a regular way, Mohamed? I mean, so now you're adding your own expertise to this when you decide what to, because there's an infinite number of changes that you can make. Do you usually do it in a regular way?
Yeah, so that's a good question. So search-based design is an open-ended problem, and you see people who are kind of going for the highest accuracy model, really injecting a lot of their local knowledge into the search-based design. So if you look at the EfficientNet search space, it's like a tweaked version of MobileNet that, they say, oh, this is more efficient in the initial layers because we can use separable const here or something. So if you're going after the best model, you do inject a lot of local knowledge. But if you are doing an open-ended investigation, you typically don't really know, and you try to just go, and put everything you're interested in knowing about, really. And so you'll see these two kinds of academic papers. Some of them are just, really going for the best accuracy, and there you really bias your search space, while others are trying to understand what's going on. And then that's where it's a more open-ended.
Very good, thank you.
So Ren Yuan says, one question, page 36. Separate combined phase. Can you explain the phase scheme once again, and how about the GPU hours for the simulation? So phase was basically, let's say I have, in this case, 10,000 steps for my search. With the phase one, what I do is that for the first 1,000 steps, I'm searching for a neural network only, without searching for hardware. And then I take the best neural network, and then I search for hardware that fits that neural network really well. And then now I have a neural network and the hardware. In the next phase, I'm optimizing the neural network only for that same hardware that I found before. And then I go to another phase. So it's like separate search, but I do it multiple times. And can you talk about the GPU hours? So here we weren't really optimizing for GPU hours. So the GPU hours is a lot, basically. For this particular paper, we used NAS search space or a NAS dataset rather. And so the accuracy values were pre-computed. What that means is that we didn't actually spend a lot of GPU time because of that, but in a more open search, then it would take much more time. So we weren't optimizing for runtime here. So, okay, I think that's all the questions in the chat box anyways, but happy to take more questions.
Other questions from the audience?
Hello, Professor. I have a question. I really enjoy the talk. Thank you so much. I'm very interested in the GNN predictor for the hardware performance. It outperforms the layer-wise model very much. And I don't know, can you share more details about the key bottleneck of the layer-wise model and the solution in the GNN predictor, such as how do you include the layer fusion in the GNN model? Thank you.
Yeah, that's a good question. So basically for the GNN predictor, we have neural network architectures and their corresponding end-to-end latencies. And so it's more of a black box prediction where, overall, if I run this neural network on my mobile phone, what is the latency going to be? So I measure it for like 100 models and I train my predictor based on those 100 models. And so it already encapsulates all of the information about, interlayer interactions and stuff like that. Whereas, but the problem is that obviously I don't want to measure all, 1 million models in my search space on that device. And so I measure it for just 100 models or 500 models, and then I predict it for the next 1 million. And the idea is that it should be accurate enough for those next 1 million models. In this plot here, I think we're training on 900 models, and we're predicting for 15,000 models. And so it works well even when training on a small subset of your search space. Whereas with layer-wise, they decompose the problem into per layer. And so there is no notion of these interactions at all. So in our, so that's the key difference. So, so Bo, I actually think I need to run. I didn't realize it's 12:18. So can we maybe cut it here or?
So any other questions? Actually, I have one follow-up question. Just
okay.
Just still about so we know that for the layer-wise modeling, so actually we only need to measure each layer. So the number of the layers that we need to measure is quite limited. While for those that if we want to use a black box surrogate neural model to predict latency, so the number of the models we need to measure, especially on the different devices, that can be very huge. I was wondering, is there any kind of good balance or the trade-off between these two different strategies?
Yeah, I think for certain hardware types, a layer-wise predictor may work well, like when it's very deterministic and you know exactly what assumptions you have between layers. But for more complex hardware, it just doesn't work from our measurements and from our analysis. Like it's just a really rough indication of how fast the model will run. And so it really depends on what kind of access to hardware you have, what accuracy of the final thing you want, and so on. But I think the way these graph neural networks or these prediction-based approaches work really well, even with a small number of samples. And there was work that built on our work that actually adapts from one type of hardware to another type of hardware using few-shot meta-learning. And so if you have a predictor already for, Samsung Galaxy S21, I think is the latest one, or 22, then you can adapt that using just 10 measured points to, I don't know, a Google phone or a mobile GPU. And so there are, there are many ways of using these end-to-end predictors really efficiently, even without many measurements. So I think even for the layer-wise one, you do need to do some measurements. And with exotic devices, like phones are an example of that. Running just a single layer can actually be already running it accurately. I mean, can already be a task of how do you feed the data into the device and how do you measure the single layer accurately and so on. And so, I think I'm a big advocate for the end-to-end, because at least if it works well, then it's predicting well. So.
Thank you very much.
All right. Okay. Thank you, Bo.
Thank you very much. Thank you. So thank our speaker and also thank everyone to attend our this week's seminar. Okay. Thank you. Have a wonderful day.
Bye.